The next question is about electrolysis. Electrolysis is always going to be related to ionic compounds. In this case, you've got copper chromate, copper being a metal, 2+ ion, and the chromate ion tells you down here is Cr. O4 2-. You're not expected to be familiar with or have heard of the chromate ion before, because you're told in the question copper ions are blue, which you probably know, but you're told that chromate ions are yellow. If you have those together in a solution, the blue and the yellow colours mixed together is what gives it the green colour. Okay, so the green copper chromate is the colour mixture of the blue and the yellow. Now, what you're expected to know though is what happens when you put an electric current through an ionic solution. Now, you've got a positive electrode and negative electrode, and you see some observations, and you're told that the positive electrode you've got it going yellow and some bubbles, and the other one, the negative one, blue, and a solid forming. So you've got to be able to explain some of those things in the next part, in the questions on the next page. So I'm going to talk you through them here. Now, so you've got, I'm only going to draw one of each just to make the point, but there'll be lots and lots and lots of copper ions in that solution there, and lots of chromate ions in that solution. The negatively charged chromate ions are going to be attracted to the positively charged electrode, and the copper ions are going to be attracted to the negative electrode, because again, opposites attract. That's all happening inside this tube. I've drawn it on the outside just for lack of space. So the solution turned yellow because these yellow ions are move towards that positive electrode, and the copper ions, which are positive, move the other way, and that's why the solution is blue over here at the negative electrode. What's slightly more complex is what's going on at the electrode when electrolysis happens, or reduction or oxidation takes place, and we'll look at that in a second. But bubbles forming over here, you've got to work out what they are based on what you know, and you've got to work out what's going on over here. We'll talk about that in a sec. Okay. So the first one I've already kind of mentioned, which is why does the colour change at the positive electrode? You have to, it's quite hard to get both marks here, but you have to say that the chromate ions, which are yellow, go to the positive electrode. That's the first mark, making it clear that this positive, or the positive electrode attracts those chromate ions. The second mark is being clearly you understand why that happens, and it's this idea that opposites attract, or negative ions are attracted to positive electrodes. So opposites attract, something like that. It's all about the electrostatic attraction of the negative ion to the positive electrode. Opposites attract. And you're told the gas produced was oxygen, so you don't have to even work that out. Oxygen is formed from hydroxide ions, and you would have covered this and seen this before, but hydroxide ions get oxidized in electrolysis. If there's no halide present, what you get is oxygen forming water, and that process releases 4 electrons. That's oxidation. Okay, so the question though is, where does the hydroxide come from? And when you've got electrolysis in solution, you've got to be aware that water molecules ever so slightly break apart, and we'll teach you more about this double-headed arrow in year 11, but you're expected to know already that water partially breaks apart into hydrogen ions and hydroxide ions, and that's the substance that makes the hydroxide. It's water breaking apart partially. How does the solid form at the negative electrode? We said a moment ago, didn't we? Go back to the picture here. It's copper ions going to the negative electrode, and the solid forming is actually copper. So to get the marks, you have to be really precise with your language. You've got to say that copper ions are going to the electrode. I'm not going to write it. You've got to say then that the copper ions turn into copper atoms. Now be really clear with your language that copper ions and copper atoms are different. So the copper ions go to the electrode, and when they get there, they get turned into copper atoms, and they do so by gaining electrons. So that actually would have got you all 3 marks. The copper ions are getting reduced to turn into copper atoms. We'll get the marks as well in words, but simply writing it as an equation is fine. The next question is 4.4, which is what would happen if you had potassium iodide solution. And because potassium is more reactive than the hydrogen ions that are in the pot, so remember electrolysis in solution, you've got the water partially broken apart into hydrogen ions and hydroxide ions, and you've got potassium iodide, you've got potassium ions, and you've got iodide ions all in there. The negative electrode, hydrogen ions and potassium ions go there. You're expected to know that if the metal, the positive ion, is more reactive than hydrogen, then hydrogen will be produced, so H2 will be produced there. The only times when you don't get hydrogen produced is if it's copper or silver. Okay, so hydrogen produced. At the positive electrode, the hydroxide ions and the iodide ions go there. The previous part of the question, we know that oxygen was formed, but if you have a halide present, you're expected to know that you get the halogen, so I2, Cl2, Br2 formed. So if the halide is present, the halogen forms, and that's the answer. So hydrogen and iodine. Right, let's move on to question 5 then. So question 5 is you've got to know about the development of the atom. This comes up quite a lot. They have given you a fair amount of information here, which is helpful. Stuff really you're expected to know. And you cover this in physics and chemistry, so it's definitely worth making sure you studied this before too long, certainly before year 11 mocks. Okay. So, you're told here the plum pudding model didn't have a nucleus. What are some other differences? Now, lots of you referred to the fact there wasn't a nucleus in your answer. You couldn't get a mark for that because it said it in the question. Let's talk about 3 other differences. And these are things, I'm just going to list them because these are things you're familiar with. You covered this in class in physics and chemistry. But you should know that the nuclear model is mostly empty space. You've got a tiny nucleus and lots of empty space around it. Okay, so ideally you would say the nuclear model is mostly empty space. You should be really clear about that if you can. And some of you were not clear about which model you were referring to. Okay, you should know a little bit about that nucleus. You're told there's a nucleus. What do you know about it? You expected to know first of all that the nucleus in the nuclear model is positive. The nucleus is positive. You're expected to know also that the mass is concentrated in the nucleus as well. So that was quite a hard one to get, but the other way of getting the mark, so there's a kind of 4th option, if you like, to get 3 of the 4 options, making it clear the electrons are not in the nucleus, they're separate from the nucleus, they're away from it, something like that. Some of you said about the electrons being in orbits or shells. That was fine, that would have got the mark as well. So it's all to do with the electrons separated from the nucleus, something like that. But many of you got the mark for saying they're in shells. Okay, so then a bit more on that then. So Niels Bohr really developed the idea of the electrons being in shells, and many of you got this actually, which was good. So you have to know that what Bohr did and what Chadwick did and what J.J. Thomson did and what Rutherford did. I'm afraid you have to learn all that stuff. But what Bohr did is he said that electrons are in shells, or electrons orbit the nucleus. It's a little bit like the previous question, which is a bit weird. The electrons in shells for 1 mark. But you had to be clear. I thought this was really hard, the 2nd mark. Some of you got it, so well done. But it's all about the fact that electrons are in different distances, in fixed distances. So fixed distances or specific distances as in the mark scheme. I prefer, though, a kind of more key stage 5 answers, that there are different energy levels. And some of you said that, which is pretty impressive. But I'll probably better stick to the GCSE answer. The fixed distances from the nucleus. Right, so then Mendeleev developed a periodic table, sorted them back in those days by atomic weight, because they didn't know about atomic number, didn't know about, we didn't call it mass number, we used atomic weight. And some people, well, the question says a student suggested Mendeleev Mendeleev reversed the order of some pairs of elements. Ah, I see. So the student suggested that Mendeleev reversed the order the reason he reversed the order of some elements was to put them in order of atomic number. But why can't that be true? And it's simply because atomic number was not known about in those times. If we go back to the previous questions, protons were discovered in the early 1900s, 1915, 18, something like that kind of time. So in 1869, protons had not been discovered. And quite a lot of you got that mark, worked that out from the information given. But you also have to be clear that atomic number equals number of protons. So atomic number of protons. Okay. And then what was the real reason Mendeleev reversed some of the pairs of elements? If you look at a periodic table and see, for example, tellurium and iodine, you'll see that tellurium is heavier than iodine, and immediately Mendeleev would have thought that tellurium should be to the right of iodine. But the reason he switched them back to as they are now, which is tellurium in group 6 and iodine in group 7, is because he wanted the properties of the elements to match others in their group, and that was the answer. So properties have to match the rest of the group. So all the halogens have very similar properties. Properties match to group or something like that. Would have got the mark. And let's do question 8 as well before I stop. So what is the state of bromine at 0 degrees and 100 degrees? Now the information is given in the question. You could have worked this out. So there's bromine. Its melting point is at -7. So anything below -7, and it would be a solid. Just like ice has got a melting point of 0, anything below 0, water is ice. Okay. So bromine's got a melting point of -7. So below -7, it's solid. Between its melting point and its boiling point, it must therefore be a liquid. So it's solid down here, liquid in between, and a gas up here. Just like water, it would be, for water it would be 0 for its melting point and 100 for its boiling point. Between 0 and 100, it's a liquid. Right, but for bromine at 0, which is in between -7 and 59, it's a liquid. So it has to be one of these two. And at 100 degrees, which is above its boiling point, it has to be a gas. So there we go. So that's the answer. Quite a lot of people got that wrong, and I think that reflects a bit of lack of patience with that question. People are probably just guessing and not really thinking about the information given to them. What is the trend of boiling points of the halogens? Look, the answer's in the question. The boiling point increases as you go down the group. So you have to say, lots of you refer to the melting point, which is a bit silly really, given it's about boiling points. The boiling point increases down the group. No knowledge required for that at all. You simply have to say what was in the question. So boiling point increases down the group, and you have to explain that. And I'm just checking the marks are going to give you exactly what you have to get for the 4 marks here. But essentially, it's the idea that the molecules, the bigger the molecule, the higher the boiling point. And you've seen this before with, for example, with crude oils. As you get longer chain hydrocarbons, the boiling point increases. Bigger the molecule equals higher boiling point. So that's the second mark. It's the best way of getting the second mark. There's an alternative as well, but increasing size of molecule as you go down the group. You could also have said the formula mass increases or molecular mass increases, but you haven't studied that yet. We'll do that next term. But anything about the size of the molecule getting bigger. And the reason that the size of the molecule getting bigger is important, just like I said in that first question I did, if you've got a big molecule, you've got more intermolecular forces, more contact points between molecules. So if you've got a long chain hydrocarbon, for example, versus a short chain, the long chain hydrocarbon has stronger forces of attraction, stronger intermolecular forces than the smaller molecule. That's the same with the halogens. If you've got little tiny fluorine, F2, versus very big bromine molecules are very big, and so the intermolecular forces between bromine and another bromine molecule are stronger. So that's what you have to say. So increasing intermolecular forces and you have to say then, so more energy needed to overcome them. And this fourth mark is very common in the GCSE. So more energy needed to overcome those intermolecular forces. This question's quite hard, I think, quite hard to get the mark for this one, so well done if you did. Boiling point of a single bromine molecule. Well, some of you got the idea, I think, that you can't boil a single molecule because you've got to overcome intermolecular forces, which means you need at least two of them. But the way that you have to get the mark is by saying something like boiling is a bulk property. In other words, when you've got lots of them. I don't suppose many people used that terminology, but there was an alternative, which is you have to make a comment about the fact that boiling point links to intermolecular forces, and so more than one molecule is needed. Try to mark this fairly generously. Really, you should be saying, look at this experiment here. You've got iron, there's the iron, reacting with halogen. Halogen being passed through in a gas. It could be something like bromine being passed through a tube, a glass tube, which is being heated up with iron inside it, like iron wool or something. It's done in a fume hood. Why? Well, because halogens are toxic to breathe in. And really, that's what the mark should be for. The halogen is toxic. Sorry about the spelling there. Halogen is toxic, or the gas is toxic, or the gas is poisonous, or the gas is harmful, or the halogen is harmful. If you said something about to avoid having to breathe in the halogen, then you get the mark. But it said ignore words like lethal or deadly, because it's not necessarily going to kill you unless you breathe enough of it in, but you have to say that it's toxic. Now, you should know the halogens are toxic. You know, for example, that chlorine was used as a weapon, chlorine gas back in the First World War. So you know link this idea with your history that chlorine is a toxic gas. Okay, so what have we got next? Explain why the reactivity decreases down the group. All right, so I'm going to start with just drawing a picture of a fluorine atom to remind you what the group 7 atoms sort of look like. Why does the reactivity decrease? Well, you have to understand that they react by gaining an electron. So when fluorine reacts, it gains an electron. The electron goes into that outer shell. So you don't get a mark for understanding that, but it's helpful to get your head around that. Now, if you compare that to chlorine, which has got an extra shell because it's one row further down the periodic table, that chlorine reacts in the same way in that it gains an electron. The electron goes into that outer shell, but that electron is going into a shell that's further away from the nucleus, right? And that's the first mark, so I'm not going to write it down, but the electron is going into a shell that's further away from the nucleus, and that means the attraction between the nucleus, which is positively charged, and that outer shell, or where that electron will end up, is greater. So that's the second mark. There's less attraction because it's further away, and so simply then that the electron is gained less easily. Just go through that again. First mark for making it clear that chlorine has got an extra shell, and therefore the electron is less attracted to the nucleus because it's further away, and so the electron is gained less easily. So understanding how they react is a nice thing to be able to do. I'm going to stop there and do the other question 8, the question 8 for paper 2 on a separate video.